Today, I'll be presenting our project, Reinforcing Good Experiences, AWAC DreamerV3 with Confidence-Aware Policy Gating. DreamerV3 is a state-of-the-art model-based reinforcement learning algorithm. It achieves impressive robustness by relying heavily on imagined trajectories generated by its world model. However, this strength also introduces a potential weakness, model bias. If the learned dynamics are inaccurate, the actor might overfit to hallucinated rollouts. To address this and accelerate learning, we introduce a replay-grounded corrective signal that reinforces behaviors that have actually worked in the real environment. Our solution is a dual policy architecture that integrates an AWAC head to leverage positive experiences through advantage-weighted learning. The key innovation is the intelligent gating mechanism, which dynamically selects the more effective policy by evaluating confidence and disagreement. This allows the system to adaptively combine the robustness of the world model with the grounded reliability of experience-based learning. DreamerV3 itself is highly general. It performs competitively across over 150 diverse tasks using a single fixed configuration. Its core component, the recurrent state space model, or RSSM, learns compact latent representations of the environment. The actor and critic networks then learn purely from imagined trajectories within this latent space. The policy objective focuses on maximizing bootstrapped lambda returns. Now, AWAC extends the Advantage-Weighted regression framework. Unlike AWR, AWAC uses off-policy temporal difference learning to estimate the Q function, which greatly improves sample efficiency. The policy update is essentially a weighted maximum likelihood regression that prioritizes real state action pairs from the replay buffer that yield positive advantages. In our approach, we integrate an AWAC head into DreamerV3. It's trained off policy using real transitions sampled uniformly from the replay buffer. Importantly, we share DreamerV3's critic network with AWAC, so the advantage calculation directly uses the learned value function. The policy minimizes the AWAC loss, and we apply weight clipping to maintain stability. Next, the gating mechanism dynamically selects which policy to use for each environment instance. It calculates a probability based on two elements: policy confidence, measured by normalized entropy, and policy disagreement, measured by symmetric KL divergence. Confidence reflects how sharp or certain a policy's action distribution is. Lower entropy means higher confidence. Disagreement, on the other hand, measures how different the two policies' distributions are. We apply a bounded penalty to discourage the gate from selecting the AWAC policy when its actions diverge too far from the main policy, ensuring more conservative and stable behavior. The final gate probability is obtained by passing the combined confidence and disagreement score through a sigmoid function. Then a Bernoulli sample determines for each environment instance whether to execute the action from the AWAC head or from the main DreamerV3 policy. We train three main components. First, the world model, or RSSM, from DreamerV3. Second, the actor-critic networks of DreamerV3. And third, the AWAC network. All three are trained using data from the replay buffer and imagined trajectories. The replay buffer stores real interactions with the environment, while the imagined trajectories come from the RSSM's world model. On the walk-or-walk continuous control task, our gated policy achieved high scores roughly 40% faster than the DreamerV3 baseline. This shows that the replay-grounded AWAC advantages effectively guide the actor towards successful motor behaviors more quickly. On DMC Cup Catch, where DreamerV3 already performs extremely well, both learning curves were nearly identical. This demonstrates the gate's robustness. It remains neutral and doesn't introduce extra variance when the AWAC signal doesn't add value. In the exploration-heavy crafter environment, DreamerV3 alone performed slightly better, and the AWAC usage ratio stayed at its lowest overall value. This highlights that the gate can recognize when the world model's planning should take priority over experience-based correction. In conclusion, our method successfully integrates AWAC into DreamerV3 through an adaptive gating mechanism. It provides clear benefits in tasks that benefit from replay-grounded reinforcement while preserving strong baseline performance in other domains. This adaptive capability moves reinforcement learning closer to general, robust application without the need for extensive hyperparameter tuning. For future work, we plan to explore more sophisticated confidence metrics and extend this dynamic gating framework to a broader range of reinforcement learning domains. Thank you.